probably sound like a broken record at this point, but I can't emphasize enough how the ideas of physics do not exist in isolation. The ideas of physics are often very, very, very intertwined and they build off of each other. And so I know, especially at the beginning of studying classical introductory physics, it isn't the most super exciting stuff in the world because when you're doing stuff like kinematics, you're essentially building tools and you're going to put these tools into your toolkit. And at a certain point, you have enough tools where you can start to explain some cool things about nature. And so, what I want to do is try to show how multiple concepts that we've come across intertwine in a way that allow us to understand why a plane can fly, why the shape of the wing on an airplane allows it to fly. And so, what I'm going to do is I'm going to demonstrate to you how concepts like force and pressure and energy can be used to derive what is known as the Bernoulli equation. And then I'm going to show you how the Bernoulli equation can allow us to understand how the shape of a wing of an airplane allows the airplane to fly. So one of the many concepts that we've encountered is this concept of work. And work is force applied to some object over some distance. And so what I have on the left is imagine those green lines signify a pipe where the width of the pipe on the left is less than on the right. So in other words, think of the cross-sectional area of the pipe on the left as less than the cross-sectional area on the right. And then I'm going to call up and down Y, and I'm going to call left to right X. And you see the blue arrow pointing to the right. We're going to assume that the fluid is flowing from left to right. We're also going to assume that the fluid is an ideal fluid, which is to say that it doesn't like bunch up in certain places. It's just a nice smooth flow through the pipe. And you see the little blue dotted lines. What I'm going to do is essentially we are going to pick on a certain volume of fluid and we're going to look at it at two different points when it flows through the pipe. So at both of those points, it's the same volume of fluid. It's the same density of fluid. What differs is that since the fluid is flowing from a more narrow region to a wider region, the cross-sectional area of the fluid is getting larger as you move to the right. And so if remember with volume, it's three dimensions, right? Length times width times height. So if the cross-sectional area is getting larger as you go to the right, that means that the delta X, the horizontal length, if you will, gets smaller. But trust me, while the part of the right looks taller and more narrow than the part on the left, that's the same chunk of water, if you will. Imagine we were putting like a tracking device on this little chunk of water, and we're going to look at it at two different times. And then the blue lines you see to the outside. Now, if you can imagine, when you have a chunk of water, it is going to experience a pressure from the water to the left of it and the water to the right of it. And so that's what essentially is applying external forces here. If you can imagine this chunk of water, it feels a pressure from the fluid to the left of it, and it feels a pressure from the fluid to the right of it. So what I did is I have a single dot that I denote. Imagine that dot is representing all the mass of that fluid. And then you can imagine on the left, there's some cross-sectional area of the pipe I call A1. And then on the right, I'm going to call the cross-sectional area A2. And so you have essentially two forces that are acting on this chunk of fluid that we are tracking. You have the force from the fluid on the left, and you have the force from the surrounding fluid on the right. And so then going back to the concept of work, so we also learned that the change in work done on a system can be thought of as the change in the kinetic energy of the system plus the change in the potential energy of the system. This is the work energy theorem. And the work energy theorem, when we looked at a conservative force like gravity, when I say conservative force, I mean that when you exert an external force on an object, there is a restoring force that acts equal and opposite. So, like, for instance, if you were trying to take an object and raise it up in the air, you are applying an external force upward in the direction of raising it. So you're doing work on the object, but gravity is always acting equal and opposite you. And so gravity is doing negative work on the object. So the net work is zero. And so if delta W equals zero, then the change in kinetic energy plus the change in potential energy equals zero. And which is to say that the total kinetic plus potential before must somehow equal the total kinetic plus potential after. They might be different in amounts, but the sum of them has to remain constant. So in this particular case, though, we have a net external work that is being done. And so more specifically, since this is moving, and by this, I mean, again, this is like this volume of fluid between those dotted blue lines that we're tracking at the left and at the right. It's the same volume of fluid at two different times. So we can say that the work being done on this volume of fluid, you have your external force, F1. This is the force that is from the fluid on the left of the fluid we're tracking. And that's moving in the direction of motion. And so we could say delta X1 is the work being done by the fluid to the left of the fluid we're tracking. Now, do you see how F2 points in the opposite direction? That's because we're talking about now the fluid to the right of the fluid we're tracking. It presses in the opposite direction. So if the force by the fluid off to the right is opposite the direction the fluid is flowing, it's actually doing negative work. And that's why I'm going to have a negative sign here. And I'm going to say minus F2 delta X2. Okay. Now, we also have a concept of pressure. And that's equal to the symbol P. And that is quite simply some force applied over some cross-sectional area. So you can imagine there's two different cross-sectional areas of the volume of water we're tracking, both on the left and the right. And so there's a force applied over cross-sectional area 1, and there's also a force applied over cross-sectional area 2. So we have two different pressures, a pressure on the left and a pressure on the right. And what I'm going to do is I'm going to, because our work equation has the force F1 and F2 in it, I'm just going to rewrite this equation. I'm just going to say that the force is equal to the pressure multiplied by the area. To do that, I just simply multiply both sides of the relationship by the cross-sectional area. And so what that allows me to do now, going back to my change in work, is I can say that P1 A1 delta X1 minus P2 A2 delta X2 is equal to the change in kinetic energy plus the change in potential energy. And so when I'm talking about some cross-sectional area moving some horizontal distance delta X, this is just a volume. The area has units in meters squared. The delta X has units in meters. And so we can just call this V1. And we can just call this V2. And so now what I'm going to say is P1 V1 minus P2 V2 is equal to the change in kinetic energy. And so the change in kinetic energy of this volume of fluid that we are tracking is going to be 1/2 mass of the fluid, which is going to be the same throughout. So I don't need to give it a number because it's just a constant m throughout. Whatever my V2 is, so that would be on the right, squared minus 1/2 mv1 squared plus, when we're talking about the difference in potential energy, we're talking about our volume of fluid being at different heights. And so we're talking about gravitational potential energy here, where you would have the mass of the fluid, G, and then whatever our Y2 is, so whatever our final height is on the right, minus mg y1. So what I've done is I've taken this concept of work and how it's related to kinetic and potential energy, and now I've written it in terms of pressures, and then the velocity of the fluid, and the mass of the fluid, and the height of the fluid. So another concept is the concept of density. And we usually use a symbol rho for that. And what density is how much mass you have versus how much volume you have. So imagine if you have some mass m over some volume, if you were to take that volume and shrink it so it was only half as much, you would have something more dense because your denominator would get smaller, and so the ratio would get bigger. Or if you had a mass m over a certain volume and then you double the volume, now your density is less because now that same amount of mass is spread out over a greater amount of volume. So just as I did with the pressure, I can also rewrite things here where I can say that the mass m is going to be equal to the density rho multiplied by v. And let's be careful here. This v is volume, not to be confused with the velocity of the fluid. So what I can do is I can take, you see the last equation I have written on the bottom there in gray? I can take this relationship that mass equals the density multiplied by the volume, and I can substitute that everywhere I see the mass m. And to even better ensure that we don't get confused here, you see how I have a volume 1 and a volume 2 on the left side of my equation? Remember, the whole name of the game here is we're just tracking a volume of fluid at 2 points. And so the volume of the fluid does not change. So I'm going to get rid of the indices. So we're just going to say it's that same volume V throughout. Now I'm going to keep the indices for the velocity because the velocity does change. Remember, on the left, you have a greater velocity of the fluid than on the right. As you can see, from the same amount of time, on the left, it travels a greater delta x1 than on the right, where it's a smaller delta x2. And that's because the cross-sectional areas change, but the volume has to remain the same. So in general, with an ideal fluid, when it's going through a more narrow aperture, the fluid flow is going to be more rapid than a wider aperture. And so I'm just going to continue with my equation now, but I'm going to make my substitution that mass equals density multiplied by the volume of the fluid. And so what I'm going to have now is P1V minus P2V equals 1/2 rho. And again, the rho is constant throughout. It's the density of the fluid that we're tracking. Whatever the final velocity, that's the velocity on the right of the fluid, is, minus 1/2 rho. Excuse me, I have to make sure I account for the volume term. So what I'm going to do is I'm going to substitute the mass. Remember, mass equals the density multiplied by the volume. And so instead of m, I'm going to have whatever the density of the fluid is. And then I'm going to have the volume V of the fluid. And then on top of that, I have another V. And again, don't get confused. This is velocity. And so we're going to say that's V2 squared. So I just simply substituted for mass density multiplied by volume. And then I have minus 1/2 rho V1 squared. What I'm going to do now, because we're getting a little bit cluttered here, is I'm going to make some more room. So bear with me for 1 second. Okay. So going back, minus 1/2 rho volume V1 squared plus, and again, I'm going to substitute for mass. So density, volume, G, Y2 minus density, volume, G, Y1. And again, this all starts with the notion that the change in work is the change in kinetic energy plus the change of potential energy. But here's the thing. The reason that I wrote it this way is because if you can see, every single term now has the volume of the fluid that we're tracking, every single one. So if I divide by V, every term, it goes away. See this? So now our relationship is P1 minus P2. And again, all I did is I divided every single term by the volume of the fluid we're tracking, equals 1/2 rho V2 squared. Again, that's the velocity of the fluid on the right, minus 1/2 rho V1 squared. That's the velocity of the fluid on the left, plus rho G Y2 minus rho G Y1. I wish my screen was just a little bit wider on the right. So I hope you're following with me, because I'm going to do one more thing. What I'm going to do is I'm going to group all of the terms that pertain to the fluid on the left side of the equation, and all the terms that pertain to the fluid on the right side of the equation. So just simple algebra here, just adding and subtracting some terms. So what I'm going to do is I'm going to leave P1 over here. But then what I'm going to do is I'm going to bring the term with the velocity one over. So that's going to be plus 1/2 rho V1 squared. And then I'm also going to bring the term that has Y1, because that's the height of the fluid we're tracking on the left side, plus rho G Y1. And that is equal to P2. So now I'm taking that P2 and I'm adding it on both sides of the equation, so it cancels out on the left and you'll have it on the right. And then you have your 1/2 rho V2 squared. Again, that's the velocity of the fluid on the right, plus rho G Y2. That's the height of the fluid on the right. So this right here is our Bernoulli equation. And so this is what's going to allow us to understand why an airplane can fly. So if you can imagine the wing of an airplane, it has a shape that's kind of like this. So it's more flat on the bottom and it's more curved on the top. And if you can imagine, when it goes through the air, some of the air streams underneath it like that, but you have some of the air going over the top. And so if you would imagine, if we were to like track a volume of air, just like we were tracking a volume of the fluid going through the pipe, the fluid doesn't break up, right? The fluid stays together, which means that the part of the fluid that's going over the top of the wing, if you can imagine, this distance going over the top of the wing is a greater distance than the distance on the bottom. So if the fluid stays intact at time 1 before the wing hits it, and then time 2, that means that the fluid part at the top of the wing had to travel a greater distance over the same amount of time. And so this is our concept of velocity. It means that the velocity of the air is greater at the top of the wing than at the bottom of the wing. So let's go back to the equation that I circled. So we have this idea of two different pressures. We have the pressure exerted by the air in the bottom and the pressure by the air exerted on top. And so with respect to an airplane wing, the horizontal distance of it is pretty negligible. It's very small. It does not factor in even close to as much as the velocity of the airflow. So what we're going to do is we're just going to ignore the slight differential changes in the height, which is to say that this term and this term in the Bernoulli equation essentially wash out, because we're going to more or less say that this height is not substantial. So now what we have, because we started with the work energy theorem, and now we have a relationship that relates the pressure on one side of the wing and the velocity of the airflow on one side of the wing to the pressure on the other side of the wing and the velocity of the airflow on the other side of the wing. We have essentially a situation here where we have to preserve this equality. So if you can imagine that the top of the wing we'll call V2 and the bottom of the wing we'll call V1. So if you look back at our Bernoulli relationship here, V2 is greater than V1. So to keep this equality that we see inside the circle here, P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. By the way, rho, that's just the density of the air that the wing is cutting through. So let's say that the velocity of 2 is greater than the velocity 1, right? So the velocity right here is greater than the velocity right here. So if V2 is greater than V1, to preserve this equality, that means that P2 has to be less than P1. That's to preserve the equality there. So what this means is, again, if V2 is greater than V1, it means that P2 is less than P1. So essentially what you have here is you have a P2 and you have a P1. That's the pressure exerted on the wing from the top and bottom, respectively. If P2 is less than P1, that means that there's more pressure going up than pressure going down. Now, what's pressure again? Pressure is force exhibited over a cross-sectional area. Well, what's the cross-sectional area? It's the cross-sectional area of the wing. So this is to say that the upward force is greater than the downward force. And this, again, is because the velocity of the fluid, in this case air, moving over the top of the wing, is greater than the velocity underneath the wing. And when we look at Bernoulli's equation, that tells us that if the velocity on top is greater than the velocity on bottom, then that means that the pressure on top is lower than the pressure on bottom. And so if the pressure on the bottom of the wing is higher, that means that upward wins, okay? There's a net upward force. There's lift. The wing is experiencing lift, and this is what allows an airplane to fly. And if you've been on a plane and been able to see the wing and you start to land, what happens? They have a flap that comes up. And so what that does is it induces drag. So what does it do? It slows down the velocity of the air that's flowing over, which now allows gravity to have its way and bring the airplane back down. But when the airplane goes up, it's absolutely because of fluid dynamics, of the work energy theorem, and of the fact that because when we use the work energy theorem to derive Bernoulli's equation, as I've showed you, when you have negligible differences in height, then if the velocity over the top of the wing is greater than the velocity on the bottom of the wing, that means that the pressure underneath the wing is greater than the pressure above the wing, which is for the same cross-sectional area of the wing means the force underneath going up is greater than the force on top going down, which means the net force is up. And what does that mean by Newton's second law? There's an acceleration upward, i.e. there is lift, i.e. the plane flies.